Markus Mueller, welcome to the podcast.
Thank you, Ding, for having me.
I would like to start with some light questions for the audience to get to know you as a person and as a scientist. If I ask you to use one word to describe yourself as a person, what would that be?
One word as a person. Human. Human.
Human, that's important.
Yes.
Yes, very scientific one.
Yeah, it comes with good and bad aspects attached to it.
Yes, most of us do. Good, and you're also a scientist. So what is something you're glad you have done as a scientist?
What I'm glad I've done. Well, I think in retrospect, I'm very happy that I had the actual chance to become a professional scientist. That was my lifelong dream, even as a child. Now it's reality, so I'm really grateful for this. So I think I'm just happy that I have this opportunity to think about topics that I find important and interesting, to choose my own topics, to really meet interesting people, sometimes brilliant people. So this is just a really good job to have, I would say.
What is the question that you're most curious about as a scientist?
Well, I mean, I would say it's about, in the end, it is about the nature of reality and our place in it, which sounds very philosophical, but I'm not a philosopher, and I think that physics and mathematics have a lot to tell there and to inform us. But it's the foundational question, let's say that. So I don't usually ask questions like, how does something work? Like, can you write down a model for something? But why? So for example, why is quantum theory the theory that describes probabilities of detector clicks? Why not some other theory? So it's, as far as possible, the really foundational questions, as far as possible as you can address the methodology of I would say, physics and mathematics.
You mentioned you've already achieved your childhood dream, having a professional job as a scientist and being able to choose whatever you want to study. So let's think ahead, say 30 years from now. What do you hope you would have achieved as a scientist?
Well, I hope that I will look back and think, oh, 30 years ago, I was really stupid. I've changed my mind on so many things. Because that would tell me that I did something right. If I just would reproduce what I'm doing now, then probably there's something that I would do wrong. But I would say if there's something that I would be really happy about, then it is finding sorts of answers of these fundamental questions that bring us a little bit forward, at least myself, regardless of the impact it has. I would just see like whether my curiosity can be, whether some answers, at least for me, can be found. I made a tiny bit of progress on the very deep questions I was interested in. That would be great.
You have something that you already changed your mind on. Is there any example you want to share?
I would say, well, one example would be my position on quantum theory. So I remember that when I started studying physics, that a friend of mine who also happened to become a quantum physics professor, David Groß, and we were really big fans and supporters of the many worlds interpretation of Everettian view on quantum theory. This has changed. I still have a lot of respect for that view. I think there are some important things it can tell us. And I respect a lot the way that its supporters just hold on to the formalism, disregarding human intuitions. I think that's an important attitude to have. But I still changed my mind more towards views that are sort of neo-Copenhagenish, perhaps, mostly for methodological reasons. So this is one of the examples. But there are many more examples and many more important examples that have to do with somehow more like the way I address questions, what I think is important, and yes. So it's hard to say.
Interesting.
Yeah.
Interesting. You mentioned the Everettian interpretation, the neo-Copenhagen interpretations. Do you mean by these cubism, relational quantum mechanics, and others?
Yes, it's a large class of interpretations. I mean, we're certainly approaching this question about what to say about interpretations of quantum theory.
Uh-huh.
Now, I would say what I have in mind here are interpretations that it's a large class of them. I'm not picking one in particular, but it's a class of interpretations where you say you should interpret the quantum state as a sort of similar thing as a probability catalog. It's probabilities of something. Now, of what? Well, the cubists would say it's probabilities. These are your personal beliefs. The Neo-Copenhagen view would say it's probabilities of measurement outcomes in a perhaps more objective chance kind of way. So I'm agnostic about the details that in the interpretation of probability we should associate with these views. But I would say that the view that a quantum state is essentially a catalog of probabilities is extremely powerful and has a lot of explanatory power. That I now hold this more like, it seems more plausible for me that this has ontological significance rather than, say, a many worlds view or other views that would see the quantum state as a sort of thing in the world, like an electric field or so. It's just sitting there, and that has an actual value regardless of whether we know it. So,
You think the averaging interpretation is less likely to be correct?
I don't think any interpretation is correct. When you say which interpretation is correct, and then somehow there's this idea that, there's this world out there, and nature itself has decided at some point which of our Homo sapiens intuitions it should pander to, right? So, is it really this like universal wave function sitting there monolithically, like we as humans tend to think about things in the world sitting here, or is it something else? I don't think nature made a decision. It's just us that we would like to have a decision because we're so much used to a certain metaphysics that's deeply ingrained in our way of thinking. But I think the idea that there's one view that's right and we have to find out which is the right interpretation and the others are not, I don't think this is the case, at least insofar as it concerns questions that are not related to any sort of predictions for anybody. Certainly you can say, here's a question: what if I superimpose a large quantum system like in Wigner's friend? What will happen there? What if that happens to you? You get superimposed and so on. And then the different interpretations may give different answers in some cases. This is the case, for example, for some of the recent extended Wigner's friend scenarios. But, well, my bet would be that probably all predictions that you derive from many worlds interpretations will in the end hold up. But I don't see any other value in somehow saying there's a metaphysically, like a distinguished metaphysical should think of there actually being many worlds in some sense, sitting in parallel in a way that resembles the table in front of me or so. It's more the question what I think is fruitful, what I would like to spend my time with, and I don't think I want to spend my time with the question which interpretation is the right one, but rather what can quantum theory tell us about the world in general, and how can it demolish some of our intuitions that we hold and tell us the world is perhaps surprisingly different from what we typically intuitively would think it is.
Interesting. That I can contrast that with another group of people interested in quantum foundations. It seems their hope is to retain the old conceptions of reality, for example, as advocated or symbolized by Einstein's position. There's something out there, whether or not I look at it. And I guess their hope is to obtain a theory as not strange as possible regarding that aspect. And your position is, do I understand correctly, is the exact opposite. You want to really demolish our immature understandings of this kind.
Well, sort of. So I don't want to say, like, I think it is important to try and see how far the old intuitions carry us. So there's, for example, the research program by people like indeed Matt Leifer, who we had last week or a couple of weeks ago, Rob Speckens, many other people in the field, who will say, let's be really careful with our claims about what is weird about quantum theory, and let's see how many of the phenomena and which of the phenomena we can reproduce classically. I think this is an absolutely important and fascinating research program. And then you find actually many things can be reproduced. Entanglement, interference, things like teleportation. You can play a game with classical coins that resembles quantum teleportation in some sense. So I find this extremely important. So you better base any claims on quantum weirdness on actual no-go theorems. You say, what phenomenon do I have in mind that I claim is specifically quantum? Can I reproduce it classically? If I fail to reproduce it, can I prove a no-go theorem that tells me that I cannot? And this is really important. We cannot reproduce a violation of Bell inequalities classically. We cannot reproduce an instance of generalized non-contextuality classically. I'm excluding lots of fine print and the definitions here, but the point is that you should have these definitions and be very clear about what you mean by that.
Sure.
And once you have that, you should really look at the thought experiments and, at the no-go theorems, and then try to see what they tell you about the world, instead of trying to like force them back into metaphysics that's classical and that's intuitive. Rather try to see what you can learn from this. Perhaps the world may be just very counterintuitive.
One place the counterintuitive features of quantum theory are manifested is perhaps Wigner's friend-type experiments, which you have studied. Why don't you tell us about your thoughts on this? For example, your understanding of the original Wigner's friend experiment, your understanding of the recent developments, and in particular, the differences.
Yes. I mean, there's certainly like one important difference is that we've learned to be careful in some respects. So, for example, in the original Wigner's friend paradox, well, you have friends, you have Wigner, you have two agents, and these agents, at some point in the experiment, they just hold different amounts of information. In some sense, the friend knows more than Wigner. So you might say, well, this kind of quantum information theoretic thinking taught us to be careful and to say certainly different agents will assign different quantum state depending on what they know. Even in the simplest case, when you just think of an entangled state and then one party has done its measurements, they would update the state and assign a different state to the other side, rather than Alice didn't do her measurement on the other side. So you might say, you might simply dismiss Wigner's friend, the original Wigner's friend, on the basis of saying, well, it's just an example of agents holding different information and thus assigning different quantum states. Let's full stop. That's all there is to say. And you find papers by, so for example, Bowles and Lostaglio that spell this out in more detail. They say, indeed, you can have a similar situation in classical thermodynamics. This has to do with Maxwell's demon. The demon knows much more than the outside observer who doesn't know the detailed microscopic positions of the gas and so on. There's nothing really surprising about Wigner's friend, the original Wigner's friend scenario. So then people were just inspired by Bell's theorem, which is really a no-go theorem of a much stronger kind. And then certainly like people like Czeslaw Bruckner were beginning to try to combine these. And so I'm really excited about the local friendliness violation no-go theorems. I think they have a lot more to say than the original Wigner's friend scenario, because you cannot dismiss those as on the basis of saying, well, different agents know different things and thus assign different quantum states. And what the local friendliness theorem tells us then is that this question, what happens to me next, is not a question that physics could uniformly answer for all observers at once. There is simply no joint probability distribution on the observations of all agents that would be derived from your physical theory and that all agents can use to predict what they will see.
Right. And do you think this is particular to quantum theory, or does it also hold for a broader class of physical theories?
I think this is a phenomenon that's at the source of a broader class of puzzles in physics and in philosophy. In this paper with Caroline, for now it's called Thinking Twice Inside the Box is Wigner's Friend Really Quantum?
Very provocative title.
Yes. The main claim is that Wigner's friend should, it's a bit methodological. We argue that Wigner's friend should not be seen in isolation as a puzzle specific to quantum theory, but should be seen in the context of several other puzzles in physics and philosophy. And I think it points us into a direction where we should seriously entertain the possibility to write down theories, to construct theories that are sort of idealistic, that tell you the very basis with which I start is the experiences of agents in a technical sense. Like, I want to be able to answer this question, what should I expect to see? Yeah. But there are many cases in which physics doesn't give you an answer to that. For example, like, experiments like somebody tells you that they will simulate you on a computer after you passed away,
Right.
or you get frozen and scanned, and then lots of copies wake up or so. Will you wake up as one of those copies, or what does it even mean? What should you believe when this happens to you? Now, the usual position is, well, these are not physics questions. No, that's philosophy of mind. Let's keep it to the philosophers in their armchairs. And let's continue and do actual physics, where we record data and frequencies and test our theories. But I think it's absolutely important, because we will be at a technological point where we have to ask ourselves these questions. And they do show up in certain corners of physics already, like in cosmology, where, for example, we ask ourselves, should I believe, like in some cosmological models, where I have things like Boltzmann brains, what should my beliefs be if I know I'm embedded in such a cosmology? How should I assign probabilities? And then you realize that physics doesn't really tell you any numbers about what you should believe. So there's a hole, in a sense, like a gap in the theory, something that it doesn't tell you. And what I think is that we should fill this gap. So I think this is an important point here. So I want to distinguish three different sorts of claims that you can make in science.
Okay.
The first sort of claims, and these are the very uncontroversial ones, are predictions for experiments that you can intersubjectively verify. You say, here's a prediction. I built this and that arrangement of lasers and detectors in my lab, and then there's a chance of probability of 73% plus or minus 1% that I will hear a click. Right? You run the experiment many times, you record the data. Other people in the world reproduce your experiment, get the same result.
Right.
You use quantum theory to compute this number, 73%, everything's fine.
Yeah.
That's the first sort of experiment. And certainly scientists should and are extremely interested in this. That's what science should be able to tell you. Now here are claims that I'm not interested in. Yeah? Many people are, but I'm not.
Okay.
And science doesn't, it's more philosophy than science has something to say about it, which is the case. Which of the, if there are empirically indistinguishable alternatives, which of them is true? So for example, two interpretations of quantum theory, I don't know, many worlds and some other thing that, like near Copenhagen, that for all experiments that you can ever do and anybody else can ever do, make exactly the same empirical predictions, is one or the other true, right? You may find this question very interesting, but the scientific methodology doesn't give you an answer, and maybe it shouldn't. Maybe, yeah. Maybe it's fine if it doesn't. But there's a third category, which is in some sense in between, and this is about making concrete, verifiable predictions that are privately verifiable. Like, for example, in Wigner's friend. If you're the friend in a Wigner's friend thought experiment, you're about to enter the box, and you're really nervous. Oh, hell, what's happening to me? I don't know. What should I believe? Yeah. A few moments later, you can verify your predictions.
Yes.
And then later on, certainly what Wigner does erases your memory and you cannot really tell what you've seen. So there's no way to for Wigner to verify this, or intersubjectively for the friend and Wigner to certify your assignments. But it's sort of still an empirical experiment that you can do, but you can do it privately.
Yes.
And I think for this, we need predictions as well. But physics cannot always give you predictions there because it's not built to do so.
Your understanding is that physics is built to make predictions for the first kind of
Yes.
The prediction that can be intersubjectively verified.
Yes.
But not for the third kind, which is privately verifiable predictions.
Yes. Yes. And this, I think, is certainly to concentrate on this first thing, like what can we intersubjectively verify, was extremely, extremely important in our in the development of science and of humankind, right? Because it allows you to bypass authority and religious authority claim. You just say, well, you may be rich and powerful, but whether your claim holds up or not, let experiment decide. And everybody can have a look and see. I can look through my telescope, and everybody else can. So concentrating on what's intersubjectively verifiable is just really important and has been. I think that now we are running into a regime where this other class of experiments becomes really important. And as I said,
just to clarify,
yes.
When you say physics is not built to answer this third kind of question, you mean it's a contingent thing? It's that physics can, in principle, develop itself to address this kind of questions, or is it just physics itself is not built for it?
Physics can, I think. So here's a possible strategy, very broad. Like the strategy would be to say, take the class of all private predictions that any observer would want to make. Try to build a theory that gives unified predictions for these private experiments and for the intersubjective ones. And what you can do is you can test the intersubjective predictions, and if they are right, then this may increase your trust in the theory also in this other regime of private predictions.
I see.
So to check it indirectly, that would be the...
Interesting. I have a question. Certainly, I acknowledge that the third kind of question needs to be addressed. But I have some doubt whether the first kind is a special case of the third kind, because it seems when anybody verifies a prediction of physics, I'm verifying it by making observations myself. I can ask my friends what they observe.
Yes.
But their answers have to be given to me through their words, through their they have to communicate.
Yes.
And then in the end, it's also my private experience to judge their what they see. And in the end, isn't everything the third kind?
So I would say yes and no. So yes, in a strictly formal reading of it is, I would say, because ultimately you can reduce the question, I don't know, of the law of gravity, Newton's law of gravity, whether that holds or some modification of it, by just basing it on what you will read in PRL tomorrow or so, right? Which is your personal experience. But that's and that's good, but that's purely formal. I'm not claiming that it has the same kind of epistemic status. Right? I'm not saying that whatever answers we come up to these types of questions should be equally trusted. I would still say we have reasons to trust much more answers that seem to have been checked intersubjectively. Right? But formally, I think they can put them in the same basket if you define them mathematically, what kind of questions you have.
I see.
And then the first person questions are just more general, and a subclass of them are the ones that you can empirically test intersubjectively.
I see. Maybe it has to do with the content of the questions. Some questions, even I have to address all the questions myself. Some questions are about other people's.
Yes.
And then there are some questions are just about my own personal empirical data.
Yes. Yes, I think so. It's an example of a regime where we run into this sort of questions like, what does it feel like to be in this sort of brain state? Yeah, that seems to be so much a kind of private experiment that you can do privately, but you cannot really share it intersubjectively with anybody. You can then report it in words, right?
Yes, yes.
But it's exactly this tension between the first and third person views that also shows up there, I think, and our kind of problems to put these two perspectives onto an equal footing, let's say that.
No, there's another question on the other side, or someone could say, I'm thinking a hypothetical realist, so to speak.
Yes.
He'll say, maybe it's because physics is underdeveloped. We can come up with better theories of physics. Well, why are you not considering the possibility that our predictions are intersubjectively verifiable? Why is that not possible?
I would say that whatever theory we come up there should certainly base its credibility on intersubjectively verifiable predictions and on their verification. Yeah. So that's what I said earlier. I said, I want a theory of this kind that makes private predictions and public ones, right? And then we can verify the public ones. And if it's sufficiently integrated and unified, and you do many special cases with a simple theory that agrees with all the public predictions, and you would say, then I also trust its private predictions.
And you're assuming there are private predictions. So this person is really nasty. Is really nasty. He says to you, what if there are really no the third kind of privately verifiable prediction? What if in this better theory we will develop everything is intersubjectively verifiable?
Yes. Well, then I would say this person is not really a realist, but a third personist. Yeah. They're insisting on a particular version of realism that just so happens to coincide with what we've done so far. Yeah. But being a realist, in my reading, so certainly you can go through all these definitions of the philosophy literature, but I think what's important is what realism does for you. Why we are realists in the first place, right? We're not realists to write it on our shirt with a big R, right? But for example, we want to say that there's no magic in the world out there. We can actually understand everything in principle. The scientific methodology is the right thing to do. It's not a miracle what we see. There's,
what's your understanding of the scientific methodology? Because some people may say, what's your understanding of the scientific methodology? Because some people may say, they may say, well, it's really about the first kind of predictions.
Well, the funny thing is that there are so many people out there that say it's about the first and the second kind, and so much about the second kind of predictions. Yeah, we want, empirical adequacy, the right frequencies of detector clicks, but we also want to really understand what's actually going on in the world, right? So the irony is that, like, so many people are really arguing for physics also addressing the second question. But they're overlooking the third, which is much more modest, which is in between the two in some sense, where it's still about concrete predictions that somebody can verify. It's just that somebody will not be the intersubjective scientific community, but whatever being or recording device or agent is involved in the experiment.
Previously, you mentioned the keyword idealist approach to physics.
Yes.
I'm curious about your understanding of this approach to physics. Would you say it's some alternative to a realist approach to physics?
So here we have a little problem with labels, I would say, right? So for a physicist, and that's what I feel like, it doesn't really matter what labels you assign to a view or how you call it. It's more about the content. But certainly when you say idealism, then it can mean many different things. And I'm advocating a certain version of that, which isn't perhaps even best called idealism. But certainly idealism is somehow unpopular in philosophy for many reasons. And I think one reason is the idea somehow when you say suppose not an external world, the physical world is fundamental, but somehow maybe consciousness or the self, or the first person, then how come that you see this world around you? That must then be a miracle, that it looks as if there's this really regular material world around you. But why does it look like that, right? So it seems that that whatever idealist position in a philosophical sense you would want to take, it has not enough predictive power, and it's not clear what you would gain from it. We would just lose a lot, I would say. What I'm saying here applies to the idea that you begin philosophically with a certain view, and you put consciousness at the bottom, and that's not what I'm advocating. Right? I'm advocating for something else, which is much more technical, which is not directly related to consciousness.
I see.
And for which you don't need a miracle. You don't explaining why it looks as if there's this external world that is very regular and so on.
Right.
But I wouldn't even call it idealism, because consciousness doesn't play any constitutive role, any fundamental role in it. But it's related to this idea that you want a theory, a physical theory in a broad sense, that gives you answers to first-person questions, that allows you in all circumstances to answer the question, what will happen to me next?
What will happen to you next?
Yes. And I've made a proposal for like a preliminary version of such a theory. We say this is where I begin. I say the fundamental claims of the theory are what happens to me next. Yeah. Now, me can mean Markus Mueller. It can mean you, whatever user of the theory, right? But
I'd say it doesn't have to be a conscious one.
Well, you have a fundamental notion of the first person or the self, but it doesn't have to be a human or biological or conscious. It could also be...
Does it have to be a biological system, though? Does it have to be alive?
No, it's just structure. So you can apply it. So I mean, so for example, so here's an example that may perhaps motivate this a little bit. So it's a very weird thought experiment, but think of it for a second. So suppose somebody would take planet Earth outside the universe, just grab it and put it on a big table to a team of scientists. The scientists know nothing about the universe, where the world, like where Earth comes from. Maybe they don't actually get Earth, but a kind of description of it, like pictures and a raw dump of all the data encoded into Earth. A long string of zeros and ones, perhaps, in some descriptional language.
The information content of it.
Yeah, it's a lot of data. But suppose you have this team of scientists. You have like 1 million scientists that have all like the tools and the funding that they want for millions of years. And the task for them is to predict what, like they're just told that, this is somehow actually dynamical, something's happening to that thing next, and they are supposed to predict what it will be. They are supposed to put a probability assignment onto what that would be in the next moment or so. So what could this team be? This team would actually have a lot of data in front of them. It would have actually fossils on Earth that show traces of dinosaurs and recordings of the sky, where it can reconstruct to a great accuracy, like that you probably are in like this 3+1 dimensional universe. We have laws of gravity and other things. So my claim is that it could probably reconstruct an extremely plausible and detailed model of the surroundings of what we think of as external to Earth, and then come up with a prediction that's pretty accurate.
Just starting from this string, which is an abstract mathematical description of the Earth itself. I have no idea whatsoever that's surrounding it. And then look at the information content of the string, trying to predict what happens to it next. Your claim is that you can infer a lot of things from it.
Yes. So then, in some sense, what you think of as the external world is some other thing that's materially surrounding Earth, is also like just logically in terms of variables, if you think in terms of data, is something that you can also reconstruct from the data that's just Earth. So you can think of it as a property of Earth. And then instead, now here are not two things. You can say, well, here's theory one. Theory one is our usual theory of the universe as it evolves according to its laws. And then I can use this theory to predict what happens to Earth next. It moves a bit further on its way around Sun, and certain asteroids will fall down, a bunch of them, small ones, and so on, right? Theory two, however, is what these scientists do. They just look at Earth in an isolated way, just the local state of Earth,
Right.
and then predict from that, reconstruct.
And they're allowed to use laws of physics.
No,
They're
no
not.
laws of physics. No, just universal induction, essentially. So a mathematical instance of like the best way to be smart and predict the future, right? So they use a formal method of induction. For example, one that computer scientists come up with is called Solomonov induction. That's a formal way to predict the next data given the previous ones without pre-assuming any laws, right?
And this is just using some sort of algorithm.
Yes. And it's guaranteed to give the right answers if what you find is coming from a computable process. And turns out that the laws of physics, as we know them, satisfy a physical version of the Church-Turing thesis, and then you can make an argument that this method, like just looking at the data and inferring with this universal method of induction, what should happen to Earth next, that this will be pretty much in line to what's actually happening to Earth next, right? So in this sense, the two theories are predictively equivalent.
I see.
And
is that a conjecture or is that a theorem?
That is a theorem. A theorem in its asymptotic version. We say if I have enough data, then the probabilities agree, assuming a version of the Church-Turing thesis. But certainly you want to know, like, concretely, if I do this to Earth and this and that resolution, will it be the case or not? So it's more an asymptotic statement in the long run rather than, you might be interested in finite, if actual finite amount of data and not infinitely many, if that works. But there's a theorem that guarantees this. And this is,
you're saying this theorem, which sounds like very powerful, it relies on some asymptotic assumption, which guarantees for you to give the correct predictions, but only in the long run, like approaching infinity.
So it is a tool that it's a tool that's discussed and used in theoretical computer science.
I see.
You can two things about to say, like, one is Solomonov induction. So you cannot really actually use it because its predictions are not computable, but you can do approximations that are computable, and then people really try to use it for actual predictions. We say, like, I don't know, if I think of a machine that learns some data, what can I predict next? And then you can use a version of that. So it's certainly a method in some sense where the first things you learn about it are asymptotic statements. In the long run, it gives the right answers, and then you try to, with mathematical effort, more and more say about the finite size things. It's a bit like probability theory, So typically say, like, 50-50 probability, what does it mean? Well, certainly there's a law of large numbers. So in those cases where you're able to repeat the experiment many times, you expect the frequency to converge to 1/2. But there are many other claims, and you can use probability theory certainly in a Bayesian way and for finitely many repetitions, or even one of them. But then it becomes perhaps more difficult, and you have to make decisions like, where's my cutoff? When in the LHC do I believe that I discovered a new particle? 5 sigma, 4 sigma, right? So it's a bit about the question of scientific practice and how to actually practically use the tool.
Yeah.
But what I said, described, that this team of scientists would give the same answers as the physical laws, that's provably true asymptotically under assumptions of a Church-Turing thesis.
I see.
Yes.
Then one wonders, if all predictions agree with the laws of physics, what's new?
New is that in this case, you begin with a situation where, in principle, every agent is alone. So it's a sort of solipsistic starting point.
It's a first-person perspective instead of a
Yes.
third-person perspective, and that's what
Yes.
you mean when we say an agent is alone.
Yes.
I see. I
So
see.
fundamental is the first-person perspective.
I see.
The third-person perspective is emergent in a sense.
Mhm.
So the argumentation goes, so what you can show is that in the long run, things will look to you pretty much as if you were embedded into some external computable process that you may call an external world,
I see.
right? Private to you, right? Then I
Okay.
can ask, well, but if I look around in my world, I see all these other structures.
Mhm.
For example, here, this Markus guy on the other side of the line here.
Yeah.
What if you are that structure, right?
Yes.
So I have this world that around me that seems to predict what's happening next. Like this Markus guy probably sees the sun set and sees that it gets dark and it will rise again tomorrow.
Mhm.
But that's something I derive from this emergent third-person perspective. What if you're actually Markus? Because then I have this first-person law that says what's happening. And then you can prove a theorem that these agree asymptotically. So they are very close to each other. So when you have a high probability of that you see Markus seeing the sunrise, then Markus has a high probability of seeing the sunrise. So it's an approach where intersubjectivity is emergent, provably so, and not fundamental.
Because it's derived.
Because it's derived, exactly. And it's only approximately true. So you have situations where it's just not upheld. And these would be exactly situations like Wigner's friend, multiplication of observers, where actually agents disagree on the probability assignment, or Boltzmann brain and similar situations, or computer simulation of agents. And this is something you mess up when you create many copies, for example. Also when you leave the notion of the formalism of probability space. So I must say that I don't know yet how to incorporate quantum theory in this approach, and all of it is preliminary, right?
Mhm.
But you can think of a situation, for example, where suppose you promised that you will be simulated on computer later on, right? And you want to ask, will I wake up in the computer, yes or no? So will I make this experience that I'm now surrounded by the simulated world, yes or no? And then in an approach like we've already argued that physics itself doesn't tell you that. It doesn't give you probabilities for this. It seems to be a wrong category of questions. But a theory of the kind I described does certainly would say, like, what would be the information content of the thing in the simulation? What's the information content that you have now? And what's the algorithmic transition probability? So you could say something about this.
I see. You say the current theories of physics don't give me predictions of this kind.
Yes.
People agree on this?
I would say, I mean, naively or intuitively would say it's not even a question about physics. And certainly to some extent that's true, because insofar as physics just demarcates a certain activity of research that we're doing, then we're not typically considering such questions. But that's more a sociological observation.
Mhm.
So I think ultimately it's inseparable, and questions of what should we believe in the case of multiplication, simulation, duplication, borders on physics, so like in the Boltzmann brain problem and quantum theory, what we learn there is that we cannot keep these regimes separate forever. In some sense, they have to talk to each other. So it's not like we can say, oh, I want to be a proper physicist, and so I decide methodologically once and for all to ignore all these questions. My claim is that first, at some point, we cannot ignore these questions anymore because they become technologically relevant. And then we realize that they're merged very much and talking very much to and are intermingled with questions that we typically consider physics in the physics regime. So we better come up with a unified approach where we try to attack the two regimes in a unified way.
How would you compare your position with the positions of cubicists? Because they seem also to take a first-person perspective.
So cubists would say that probabilities are always to be read as subjective beliefs. For me, probabilities I'm talking about are private chances, objective private chances. So for example, my claim would be that if you're faced with a very exotic thought experiment, like, being simulated in a computer tomorrow or in 10 different slightly modified versions of yourself, then the question of what happens to me next does have an objective answer in some sense, in the same way as it has when you enter a physics laboratory and ask, will I see the stone fall down or the detector click? Whereas the cubists would say, there are no probabilities do not exist. Quotation Bruno Definetti. Yeah? And they say probabilities do not have any ontic hold on the world. And actually we want to say and learn something about the world, what's actually out there in the world. But we do this tomorrow because today we're talking only about the quantum state and it has no ontic hold on the world.
Do you ever discuss with the cubists on this disagreement? What do they say to you? What do you say to them?
Yes, I discuss with them a lot, and I have a lot of respect for what they're doing. In some sense, I feel like a brothers in spirit with them, right? And some things about, like, some views overlap a lot, like the view on the quantum state. Certainly, we both, like, we see the quantum state as something that pertains to an agent.
Yes.
And that is about probabilities of future observations.
Yes.
The disagreement is then more about, is it objective, is it subjective, like, is it a belief, or what is it actually?
Do you think there's an edge to take an objective view on the probability in making progress in physics?
Well, if you want to do something like what I want to do, then yes, because my claim is that there are only private laws, and this is what hits you, right? The external thing, the laws externally that happen to you, that just depend only on your state. So when you compute these probabilities, depending on your state, they cannot be subjective. There must be some aspect to it that is objective. Otherwise, there would be nothing that would take the place of the external world, the thing that actually hits you when you kick it. Right. Like, you will probably fall down when you jump out of the window, even if you believe you fall up, right?
Yes.
And so there is something to, like, and I think that also is true for these thought experiments where somebody tells you tomorrow we will simulate in a computer. Somehow the world will hit at you, and there's something to be said about what that will be, even though it may not be deterministic. But something like a probability or something weaker that's objectively there about what you should believe. And that's, I think, the main difference to the cubists. And the cubists pay the price for being subjective. They do not, and that's not, they don't even claim to, but they're not saying, here's why we have a world around us in addition to our beliefs, right? They just take that for granted. Say, here's a world and I should find my way, and then I do it by assigning quantum states. Whereas what I do does that. It tells you, it gives you exactly a statistical reason for why we see a world around us. Yeah. So that's a big difference.
This is a construction in progress. You said currently you don't incorporate quantum physics. Is that right?
I don't. So what I should not do and do not want an approach like that to do is like to say, oh, here was version 1. It's about probabilities. Let's do version 2. It's about quantum states and make it quantize it, and then wow, and that would be stupid, right? You want to test your approach, and ideally what you want is that your approach predicts aspects of quantum theory. You want to reconstruct quantum theory from your assumptions. And that's a much more difficult thing to do. And when you aim for that and you can do that, then it's a much better sign of health of your assumptions, rather than you import all the other things I know about physics, and then I have this new theory and I can do whatever I want. That would just not be interesting. Ideally, you want to start with as few assumptions as you can and derive as much as you can from it. And in my earlier paper, I did already an attempt to argue why statistically, just from this fact that there is no encompassing Kolmogorovian probability space typically from more than one observer, why some aspects of quantum theory could perhaps be seen, like no signaling but Bell violations, but this is still speculative. But this is something one should aim for, I think.
To the audience who feel very sympathetic to your pursuits, what would you say is the most rewarding challenge to think about?
Rewarding challenge. So what do you mean?
What's the challenge that once it's solved, it's much progress for the program?
Right. So at the moment, it is a technical challenge. So it's really about the way that Solomonov induction has so far been phrased and treated, which is basically as you think of an agent that learns one bit, then learns the next bit, and learns more and more bits. But you want a version of it where you can have a sort of forgetting of information, right? That's a technical thing. That's something that I'm working on at the moment. It has to do with progressing algorithmic probability and universal induction. But then what I try to do in parallel, and this is a lot of fun and open to less technically inclined people, is just to say, let's consider just a very broad class of theories along these kinds. We say, oh, let the first person be subjective and something of the sort that I described roughly. Yeah. Then what is it like? What's this worldview? What's going on? Like, how should you think of causation? And you have very fun phenomena. For example, you're this agent. According to this theory, the fact that you see the sun rise tomorrow is just due to the fact that you hold enough information in your brain that you can reconstruct the fact that you live on this planet and the laws of physics and so on. But now a stone falls on your head and you lose almost all your memory. Right? So then one prediction here would be that the laws of this universe become ineffective for you. You sort of fall out of the universe, right? Because there are no laws, right? It's just reconstructed for where your information content is.
Yeah.
And if it's diminished by a lot, then something else will happen. So it's if you're absolutely not technically inclined, you could do a science fiction book where like a bit like Permutation City, but much more crazy. Where you say what would be the consequences of such a view, and the claim is you would be able to answer lots of questions that you couldn't otherwise, like how much money should you pay for your computer simulation 100 years from now, or should you believe your robot's one brain? But it will also be extremely counterintuitive in many exotic situations.
Well, how do I view death in this scenario? Is there afterlife, or does the world just end?
It depends on the details of the formulation. So one possibility is simply that you've been like that death in the usual sense is not like is subjectively not a thing, right? So I don't want to like start speculating here a lot, but that's a statistical phenomenon that I call probabilistic zombies in my paper. So here's the thing. So as I said, like when I look at some other structure, like I'm here, but I also see ding Jia, or at least I can infer that ding is somewhere in the S at the moment, and I assign probabilities to what will happen to ding tomorrow, then this is the same probabilities will actually apply to ding. Yeah? I would say there's an almost 100% chance that you will see the sunrise tomorrow, and indeed for you there is an almost 100% chance that you see the sunrise tomorrow. But in some cases it's not true anymore, and this is if you lose a lot of information. So then certainly I will see ding disappear, but what happens to ding subjectively is a completely different question. You would the theorem that would guarantee the applicability of the third person view would then just lose its applicability. Right? And you would certainly sort of drift off into another, well, I wouldn't find you in my world anymore. We wouldn't agree on what we see. So this is one possibility, and the details depend on the details of the formulation of your theory.
I see. So should I understand it as saying, once we understand the theory better, I will have an answer?
Yes, certainly. So when you say you have, so I described the approach as, and like hoping to say something concrete about these exotic puzzles like Boltzmann brain problem, multiplication of observers, computer simulation of agents, Wigner's friend, and then certainly termination is yet another situation that isn't so different, right? It's a situation where the theorem in my approach, which guarantees intersubjectivity, just loses its applicability. So yes, indeed, the question is what happens to me when I die is yet another question that I hope to address with this approach. Yeah, but it's too emotionally laden to start with this. So I want to exclude it because the danger is it's too dangerous to wanting to fool oneself, right? Yeah.
Yes, I understand. Okay, that's very interesting scenario. However, I can imagine that if it is true, if it turns out that it describes our world perfectly, it'll be disappointing for many people. I'm not sure what Matt Leifer would think about it. Do you think he will be very disappointed because that means much of his pursuits in physics is a waste of time?
No, not at all. I mean, first of all, I must say, if Matt is disappointed because of what I'm saying, that would be a huge success for me. I think it's much more likely that he thinks I'm completely crazy, right? And that's certainly a possibility. Yeah. Mm-hmm. As I said, I expect that 30 years from now, most of the things that I believe today turn out to be wrong, and I may just be completely wrong with everything I say, and that's why I try to put it on as rigorous formal mathematical footing as possible. But it doesn't undermine the efforts that physicists that do about like what we can say about quantum theory. Certainly not, and the interpretation of quantum theory. It's not like, so for example, like at some point we found like water. Is water a fluid? Well, at some point we learn it's actually molecules, so it's not a fluid all the way down, but this is irrelevant for people who swim in water, certainly. So however, I guess a view of the kind I sketched would tell a very different view of the world, in the sense like, here's something that gets demolished right away, and that the idea that there's this one world, our universe, perhaps in many Everettian branches or so, but it's this one world that's actually realized. All other possible worlds are not actually real. It had an actual beginning in time. It will unfold and at some point perhaps end or go on forever. And this is the view, and it comes with lots of ethical implications, like the now closed Future of Humanity Institute would say, well, if this is the case, we should invest a lot of effort into actually colonizing the galaxy to enable the possibility of life, as many human lives as possible, and so on. So there's a lot of ethical and decisional and baggage associated to this particular worldview of this one material universe sitting there, one realized, the other's just possible, and everything else deriving from this God's eye third person view where we're just embedded in it somehow and we flow with it. That would not be the case, because in some sense, everybody of us would somehow, perhaps, depending on the version of theory, do a never-ending random walk on the possible modes of being and find themselves in one world and then another world. And so it would be a very different view of the world, and perhaps with different ethical implications, perhaps. Yeah.
So some people say that they will celebrate the success of quantum foundations once this discipline of research is dead, because then that means we would have solved the problems of the discipline. To you, what would be a good point to celebrate? What's the success someone who's interested in quantum foundations should aim for?
I'm already celebrating. I'm celebrating that it went from a stage where a lot of effort was put into the question of interpretation to more fruitful pursuits that are related to quantum information theory, up to a point where one of its advocates, Anton Zeilinger, actually got the Nobel Prize. We learned so much. We have Bell's theorem. I think I'm just very happy to live in a time to be one of the human beings who know Bell's theorem. What a profound insight into the world that like millions of years of Homo sapiens didn't have that. I think we have all the reasons to celebrate, and we should have indefinitely Quantum Foundations conference to celebrate and make more progress.
Well, what are more progress?
Well, that's different for different people. So there are so many things to think about and to discuss. And so certainly some of my colleagues, not so much me, but they are thinking about more general causal scenarios. Instead of Bell, you think of triangle scenario and others, and ask, what about non-classicality in these scenarios? What can I do with it? What can I learn from it? This is super fascinating. I personally think that quantum foundations can be relevant in understanding quantum field theory better and perhaps quantum gravity. So one of the things I'm interested in is whether we can somehow understand part of the structure of quantum theory just from the structure of space and time. So this brings you into a program where you study boxes that you can rotate in space and ask what correlations that are possible with or without quantum theory and so on. And so many other things that are interesting, fascinating to think about, and that improve our understanding of the structure of our world, I would say.
Do you think quantum theory will turn out to be wrong, like classical theory?
I mean, I don't know. Certainly, I don't know.
What's the chance in percentage?
Yeah, I thought about this at one point, and I think my Bayesian probability assignment would be something between 10 and 50%, that at some point we will discover relevant deviations from quantum theory. And with these, I don't mean like boring deviations. Like take Jonathan Oppenheim's fascinating work, which I find absolutely thrilling and interesting about, maybe gravity is classical after all, and it interacts with quantum theory in a probabilistic way. You could say, in a way, if this turns out to be true, that's a deviation from quantum theory, because then space and time would not be really quantum. But I don't mean that. So that still would fit exactly into the same Hilbert space / completely positive maps framework that we have so far.
Yeah.
But say, beyond like beating the Zittelson bound, finding other correlations or probabilities that don't really fit the Hilbert space formalism. I don't know, something between, 5% and 50%. I don't know. Like, not at all something I would bet too much money on, but certainly something that's possible and that we should examine and that we should test in experiments.
One possible way of having quantum theory as an approximation is to say collapse models are the correct theories.
Mm-hmm.
People have different credences in the chance of this. What about you?
I think so. It's good that some people are thinking about this, and it's very good to do experiments and to try to rule out parameter regimes and so on. But honestly, personally, I don't really understand that it's so popular. To me, it's like, oh, you have quantum theory, you have all these puzzles and paradoxes and these enigmas, and you kind of sweep them under the rug dynamically. You say, yeah, we don't know what superposition means, but let's just assume it disappears quickly enough. It's a bit like saying, I don't know, we have relativity theory, and we don't want this relativity of simultaneity. So yes, there is absolute simultaneity, but here's this extra mechanism that hides it, right? So I don't know. To me, it doesn't have the ring of truth. I don't see like a compelling idea or like To me, actually, it's a personal thing, like certainly personal taste, but
Is
I
it
really like
aesthetic?
ideas that are counterintuitive, let's say that. And it's
I
too
see.
intuitive that things just, collapse away that, I don't know.
I see. What about Bohmian mechanics?
Yeah, same
Same.
thing applies there. You introduce unobservable, like claims that are unverifiable to tell a story that makes you feel more in line with your classical worldview.
Mhm.
I don't see why you should do this. The whole appeal, even why I find quantum theory interesting, is that it's not just about the particles moving and the old boring billiard balls and point particles of classical physics and things actually sitting there. So, I mean, I'm not claiming that I know what's right or wrong. So there should be people doing Bohmian mechanics, many of them, and I know some of them, and I like what some of them are doing.
Mhm.
They should go on with the research. Tomorrow it might turn out that they were true and I was wrong all along. But
Yeah,
for my taste of science, it doesn't appeal. Like you introduce additional claims to fit a certain interpretation that you would like to have. That's, I don't know.
so some advocates of, for example, objective collapse models,
Yeah.
Bohmian mechanics, they think their theories have one good point, which is that they don't suffer from the measurement problem. And are you bothered by the measurement problem of ordinary quantum theory?
I would go with my colleague Mike Cafaro and say that the measurement problem is a feature and not a problem, because it's the thing about quantum theory which tells us most clearly about where our intuition goes wrong. And the intuition is exactly that there's this thing sitting there, which is the world, and you can have a God's eye view on it, which is just describe it from a third person perspective, and then that's it. That's all there is to say. The measurement problem tells you, like, you have to say more than that. And the first reaction would then be, well, this is not what we had to do in physics before quantum theory, so now we have this problem. But it's so for me, it's a great feature in the hint to a different metaphysics. It's only a problem if you stick to sort of metaphysics that's classically motivated. I mean, there's a lot of fine print, right? And I could discuss for hours now what the details of how my view can be substantiated or not, right? But
yeah,
I'm more saying here a bit colloquially that that's my feeling about